Okay, in this lecture, I just want to have a look at the regioselectivity in elimination reactions. And to do that, let's just look at an example of a dehydration reaction. So this is it. If we look at a reaction like this, and I said it's going to be a dehydration reaction, but of course we should have been able to work this out. So that's obviously a type of dehydration reaction. And so if we use our acronym of battle, we can see that an elimination reaction is definitely okay mainly because of this acid bit over here. So the acid is the thing that's going to be changing that. We don't have a strong base, so in this reaction over here, we're definitely not going to be doing an SN2 reaction, all right? There's no strong base, so or bulky base, so we are certainly looking in that kind of that range, but we don't have a leading group at the moment. But the fact that we've got a very strong acid over here, which is present, is the thing that is pushing it towards an E1 type of reaction. So we're certainly going to get that protonation step happening. So we recognize we've got this acid, nice strong proton over here. That makes the oxygen the base. So it's going to pick up a proton, one of those. I'm not showing the bond breaking, but we're going to get our protonated alcohol, which is now our very good leading group. So we are now set up for the formation of a carbocation intermediate, which is really the example of why we're kind of pushing towards an E1. And then, well, the other thing that we're looking at over here is that we're heating this thing up over here. And the heat is certainly something that's going to be pushing towards an E1 as well. Much like our substitution reactions, we mustn't forget that as well. Of course, this is a tertiary carbocation that would form, and that's also quite critical to make sure that we getting a very nice E1 reaction occurring. So of course what needs to happen is that this leaves, and let's not forget that these are equilibrium, and the water leaves and we get our tertiary carbocation intermediate that's formed over there. So we've got this tertiary carbocation intermediate, and we know it's going to be a dehydration reaction because the counter ion to this, the counter ion of this strong acid is a very weak counter ion. It's an O- counter ion, which is significantly resonance stabilized. Remember, we can draw that out. And so you can see this negative charge can delocalize over 3 oxygen atoms, much like sulfuric acid can, sulfate anion at least of that. And so this is a really weak nucleophile and not suitable at all for doing an SN1 reaction, a substitution. So dehydration is definitely the order of the day here. The big question, of course, is in the next step, we need to remove a proton. And the thing is, there's actually 2 places where we can remove protons. There's 3 protons here. If we take this proton away, we're going to generate a molecule that looks like this. The product would look like that. So the double bond would be on the outside. So that would be if water comes in and picks this proton, it kicks in and we get that. The other alternative is that we've got 2 protons over here and 2 protons over there. And so if we take one of those away and we kick in, we're going to get the double bond on the inside of the ring like this. Now I'm hoping, so I'm going to put an or there. I'm hoping that you recognize that whether we come from this side or from this side in terms of the proton, do we take a proton from here or take a proton from there to form the double bond, that generates the same product. So there really isn't any difference from that. But these 2 are definitely constitutional isomers of each other, and they're different products. And there is a major and a minor product that forms in this reaction. And the major product is this one over here. How did that happen? We just draw it out. It's the water that was given off actually, or some water that's around, picks up that proton and we kick in and we form the double bond like that over there. All right, so what is the major product and why is it? So there was a rule that was developed by a Russian gentleman, and the spelling of his name is like all over the place in the literature, mainly because his name was written in Russian, and so it has to be sort of transliterated. But the one way that is accepted is this way. His name was Zaitsev, and it was called Zaitsev's rule. And Zaitsev's rule essentially says that when we do elimination reactions, that the major product is the double bond that is the most substituted. Let's write that down. Now, the reason for this rule is not something that I'm going to go into any detail in this course with, because you have to look at kind of like the 3D geometries of the transition state of this over here. But essentially, it is a well-known principle in organic chemistry that a triple bond a tri-substituted double bond is more stable and more and less reactive, or no, it's actually more reactive, but it's more stable than a di-substituted double bond. And so this is a principle that comes in. It has to do with the arrangement of the orbitals, but we're not going to cover that in this particular course. So this general rule, Zaitsev rule, is one which we will follow in terms of just this is the major thing for all kind of elimination reactions. However, there is a little bit of a twist, as with all things. In this particular case over here, it's an E1 reaction. I want us to look at the same thing, but now as an E2 reaction. All right, in this reaction over here, if we analyze this over here and we decide what's going on, so we use our acronym and we have a look at this. Is elimination a possibility? And the first thing is that, yes, we do have a leaving group over here, so that's great. And we also have a nice strong base over there, so those kind of things are present. So definitely elimination. We've got beta hydrogens next door on that side and that side over there. And we've got a very strong bulky base, which is really kind of the absolute cliche in terms of an E2 reaction. So I mean, even at this point, we can say, yeah, this is going to be an E2 reaction because of that. There are, of course, other things that we need to look at, and there's no acid. The temperature is room temperature, which of course doesn't necessarily say that it's a substitution just because at room temperature. This part over here, the fact that we've got this very strong base, means that we've got to do that. Also, the leaving group is on a tertiary center, and there's just no ways that we're going to get any kind of SN2 type reaction occurring over here. The most likely, like without any kind of doubt, is going to be an E2 elimination. So this would result in two different products, which are identical to the two different products that we had in the previous example. So those are the two products over there. Now, Zaitsev's rule would say that this is the major product over here. But it turns out that in this case, it's wrong. Zaitsev's rule is not right. This, however, ends up being the major product, and this one ends up being the minor product over there. So what's going on? Well, this is actually quite easy for us to understand. And it has everything to do with the fact that the base over here is extremely big and bulky. Now, because it's extremely big and bulky, it needs to come and get one of the protons that are available. And its options are one of the two protons here, one of the two protons there. They're identical to each other, so that gives us that product in any case. Or one of the three protons, which is on this carbon over here. Because this is big and sterically bulky, the most accessible protons are the ones over here. And that means that they are the ones that are going to be picked up, which explains why this is the major product over here. This rule is attributed to Hoffman's rule, and essentially it says that when we have an E2 reaction with a sterically bulky base, that base will go to the least, or should I say the most sterically accessible hydrogens. So I think this is kind of makes sense, certainly in my head, that, I mean, if you've got something that's really big and bulky like this, that it would want to go to the sterically most accessible kind of position that is possible. What it does mean, though, and it is something that we see, is that if we do this type of elimination reaction, we can actually favor Zaitsev, but it means we can't use a sterically bulky base. And so if we change the conditions, we can actually favor this way. So this is what it would look like. In this case over here, if we change the base now to something which is actually quite small, and so it's not as sterically bulky as the tertiary butoxide, then what we end up is Zaitsev rule starts to take place, which is the main dominating rule, is that we get those sorts of as the major product. Really, Hoffman's rule only comes into place when we've got a sterically bulky base and we're going through an E2 mechanism. So here, it's unlikely that we actually really need to heat it up that much. I just put it there just to kind of point that elimination reactions are typically done at higher temperatures, but we won't have to actually heat it up that much. We're certainly never going to do a substitution reaction on here. Absolutely not. As a tertiary leaving group. So this has to be an elimination reaction, which would give this as the major product based on Zaitse's rule. So overall, what we've looked at in these two reactions is what we call regioselectivity. And the regioselectivity essentially is when it's the region of the base that is going to pick up that proton. And so we have these two different products that get formed. And this principle of regioselectivity is actually much bigger in organic chemistry. But in here, in the context of elimination reactions, it's which double bond forms. And that really depends, as I say, a lot on the substrate. Are there two options that are available? Sometimes there's not. So then there is no possibility of regioselectivity. But in this case over here, there's a number of different positions. Those two are the same. That one is different, and so we get these options. Zaitse's rule says that the most substituted double bond is preferred, and Hofmann's rule says that if we're using a sterically bulky base in an E2 reaction, then we are going to favor the least substituted double bond effectively. Now I want to talk about stereoselectivity in elimination reactions. So here's another classic example of a dehydration reaction. Hopefully we're starting to recognize these types of reactions, that this is certainly going to be an E1. So if we look at our acronym, why are we happy that this is an elimination? The first thing is, of course, that as it stands over here, we don't have a good leaving group, which is the big problem. However, we do have a really strong acid that is present. And this acid, by the way, often we see things like that, it only needs to be in catalytic amounts. But what it needs to do is protonate the alcohol. When it does that, it makes it into a good leaving group. And so we do have a good leaving group, and we've got beta hydrogen, not on this side over here, but we do have one carbon next door to this OH over here, which means that it's a possibility of an elimination reaction occurring. So this is quite likely. We've also got a lot of heat going on over here, which is looking good for that. So we got this acid, and the acid is certainly something that we connect with in terms of making a good leaving group from an alcohol, and that's almost certainly going to be an E1 reaction. The temperature itself is also pointing towards that. So we've got this E1 reaction that's occurring over here, and we can go through that mechanism where we would protonate this, makes a good leaving group, it leaves carbocation forms. Then the ethanol, we don't have water present, or the water that's given off could be used as well, I guess. Ethanol comes in, picks up one of those protons, and they would leave. And so we're going to form a double bond. So our inclination, of course, would be to draw this as the product. All right, so we got that product over there. But the question, of course, is why was this the product and not the other alkene where the double bond is now like that? So if you remember correctly, we talked about this being a trans double bond. That's very common, but it's probably better to talk about this being the E double bond, and then this one we'd sometimes call about cis because there's two hydrogens on the same side, but it's better to refer to this as the Z double bond. So there are actually two possibilities over here. Which one is preferred? And it turns out this one is the major product. Which leads to the principle of stereoselectivity. So what we're doing here is that obviously in an elimination reaction, we're forming an alkene. That means that in terms of stereochemistry, what we're talking about here is not ROS, because those are on carbons that have four different substituents on them, but rather double bonds. So whether we get the E or Z isomer that's being formed over here. And the simple rule is that the E product is the major product. Now, why is that the case? To do that, we need to kind of look at the carbocation intermediate. So after we lose the water, so minus H2O, so that it's left, we end up with our carbocation, which would look like this over there. Now we need to remember that the carbocation itself is actually flat. And in the next step that needs to happen is that one of these hydrogens needs to be picked up by a base. It could be the water that's present, of course, that was given off. It needs to pick up that, and those electrons need to kick in here. And here's quite an important thing, and I'm going to use this example to start with, because when we look at E2 reactions for stereoselectivity, it's even more important to kind of see this. But for those electrons to donate in like that, the orbitals need to align. And this is where a Newman projection is actually going to be very helpful, to look down this bond and to see what's going on. It's a bit of an odd Newman projection. So we're going to stick our eye here and we're going to look down this bond. And what are we actually seeing? So as we look down that bond over there, this carbon over here, this carbocation is flat. So there is a hydrogen sitting out planar to this. So we've got something that looks like this over here. We've got, as we're looking down that bond, the phenyl is on this side over here, as I see it, and we've got that. And then at the back, we've got the other carbon, all right, which we draw like a circle like that. And what we see is the methyl group is sitting somewhere over here in the same plane, and that means the other bits are here. So this is our CH3, and the two hydrogens that are there are in this position over here. All right. Now, this is a carbocation. The carbocation is actually in a p orbital. So we're looking at it straight up and straight down like that. There's the p orbital that's sitting over there. And of course, it will be shaded on the one side and not. Now, in order for the elimination reaction to occur, this sigma bond, all right, we've got two hydrogens here, but one of those hydrogens has to get coplanar with this p orbital. In other words, this whole thing over here has to spin around a little bit just to get this coplanar. It's very close. The way I've drawn it over here is very close. But it really needs to get to 90 degrees so that the electrons that are in this orbital can overlap with this empty p orbital and then form the double bond. And for that to happen, we're going to have two kind of extreme transition states that could happen. So the one is very close to this one over here. So I'll draw it out. We have to do that again. And the other one looks like this. So because this bond over here can rotate around, there are two extremes that can happen in terms of the positions for that elimination to occur. The one is where these two groups over here, and I'm going to just mark them in green so you can see them, the phenyl and the methyl, are far away from each other. And the other example that elimination would occur is when the phenyl and the methyl are close door to each other. Now, the thing is that when they're far away from each other, this is the lowest energy transition state that would happen. There's no steric kind of clash between those two parts. They're far away from each other. And the only thing that this is clashing with is a hydrogen, which is very small. And the only thing this is clashing with is another hydrogen, and that's also very small. In this situation over here, we've got this phenyl group, which is big. We've got a methyl group, which is big. They're clashing with each other over here. And so if we eliminated this point over here, so this proton leaves, the phenyl and the methyl will be on the same side, just like we have over here. And that, this, because of this clash, means that this transition state that we've done is a high energy transition state. So elimination reactions tend to be stereoselective for the E double bond. So E1 reactions are stereoselective for the E isomer. Now, this term stereoselective is actually quite an important one here for us to consider. Stereoselective means that when presented with two stereochemical outcomes, one of them is preferred. And this one can be explained in terms of being preferred because it's at a lower energy. A trans double bond or an E double bond is at a lower energy. And that comes from the transition state, this carbocation, which is flat, where it wants to have the two bigger groups as far away from each other as possible. Okay, now we need to look at E2 because something very special happens there. So if we look at this setup that I've got over here, so we just put in our favorite base for doing an elimination reaction, an E2 elimination reaction. One of the things that we, up until now, if we drew this out, we'd say, okay, the base comes in, it picks up that proton over there, it kicks in the electrons, and it kicks out the leaving group. And that seems absolutely fine. For those of you who know, what I've just said right now, at this very instant, was complete nonsense. It is correct that the base needs to pick up the proton. But here's one of the things that's very important in E2 reactions. These are just like SN2 reactions. In order for the elimination to occur in one step, which is what an E2 mechanism must be, there has to be alignment of orbitals. And the key thing here, this is extremely important in an E2 reaction, is that the leaving group and the proton that leave need to be anti-periplanar to each other. What it means is what I've drawn over here for in this conformation of this molecule, and we'll get to that now, the proton and the leaving group have to effectively be on opposite sides to each other. Now, the only way that we can see this nicely is through a Newman projection, which is why drawing Newman projections is so important in this course. So if we look down this bond over here, so we can look down here, and we draw out that Newman projection, this is what it would look like. All right, so this is the Newman projection that I've drawn. Just to help us track everything, I'm going to put this other proton here in blue, just so that we can see the difference between the two. See, this H is on the top face, same as the bromine, they're on the same side. So here's the thing. You see, when this reaction occurs, what we want is the O tertiary butoxide needs to come and pick up this proton. But at the same time, the electrons that are in this orbital over here need to line up, all right? They need to line up so they can form a pi bond. So what's going to happen is that the electrons in this orbital over here that are lined up over here need to be anti-periplanar to the leaving group, because the orbital here, those electrons in that sigma bond, need to overlap with the antibond of the bromine. So they've got to be lined up like that. And if they line up like that, it means that you can pick up the proton. This thing kicks its electrons in. It's hiding in between because this is a carbon, that's a carbon. So it's forming a double bond there. And this one would leave like that over there. This proton cannot leave. It is impossible, totally impossible for a base, any base, to pick that up and for an E2 elimination to occur. This blue proton cannot happen in that way at all. Now, in this particular example over here, whilst I say the blue proton doesn't want to react, that's because this over here would be the lowest energy conformation. So look here, we've got the phenyl and the methyl, they're opposite each other, we've got the bromine. So what's happening is, in terms of this conformation over here, we don't have these two as far away from each other as possible, and so that's what's going to happen. There is, of course, another conformation. I can redraw this so that I get the bromine over here so that it is anti-periplanar to that H. So let's look at that conformational change, which would be kind of like an equilibrium as it's turning around. So I'm going to keep the front exactly the same, and it's only the back that I'm going to change. So the bromine is going to move to this side. That means this H goes down and this phenyl goes up there. So the bromine's on this side. So in this reaction over here, if a base comes and picks it up, it can no longer pick up the pink one. It would have to pick up the blue one. And the product of that would be not the trans product. So the major product over here would be the E product over here, or trans. This is major. And the minor product would be the Z product over there. All right. So if it did this. However, I hope you appreciate, though, that between these two things over here, we've got a bromine and a CH3, which are kind of clashing into each other, but a CH3 is pretty small. And over here, the phenyl and the CH3 are far away from each other. Over here, we've got the phenyl and the CH3 clashing into each other, and the CH3 and the bromine clashing into each other. So this is a minor conformation. And this would be the preferred one. Now let's go back to the point here of this being stereospecific. All right, let's look at this in terms of being stereospecific. The reaction is stereospecific because the proton and the leaving group have to be anti-periplanar to each other. In this particular example, if this thing spins around, there are two different conformations that would form, and the reaction will occur stereospecifically, but it will actually give a major and a minor product over here. There are two possible products. So it is selective for the major because there is no alternative. What I want to do now, though, is I want to show us another example, which is an upgrade of this, and show how the stereospecificity of an E2 reaction comes into play. So in this example over here, again, it's so similar. There really isn't anything exciting about that. We've got this leaving group. We've got a nice sterically bulky base. It's going to be an elimination reaction. That's all fine. But if you don't follow the fact that this needs to be an E2 elimination, which means it's stereospecific, you're going to give the wrong answer. Because what you're going to do is you're going to say, oh, there's a proton over here. It's going to eliminate. And you're going to say that the product of this reaction is this one over here. Form the double bond, and we've got this OMe over there. You can say that's the product of the reaction, and that is actually a product that does not form at all. The major product of this reaction is this one over here. I used the wrong term. I said major product. It's the only product. Why is that? It's because of the E2 elimination. And in order to answer a question like this, we have to go through a number of steps to get this right. And really, the best way of doing this is via a Newman projection. Now, it doesn't matter which side you look down. Whatever's easiest for you is okay. I'm going to look from this side, looking up like that. And so I'm going to draw out the Newman projection as I see it. All right, so there's my Newman projection. I can see there's my bromine, my leaving group. And if I look at this Newman projection over here, I have one serious problem in terms of what's going on. The bromine, the leaving group, and the proton are not anti-periplanar. This conformation that I've drawn over here will not result in an elimination reaction. All right, that's quite important to realize. It doesn't matter that we've got a good, strong, bulky base. It doesn't matter that we've got an alpha beta hydrogen, which is beta to a leaving group. In this conformation over here, which is the preferred conformation, make no doubt about that. The bromine and that together, the OMe and the phenyl are together like that. This is absolutely fine. What needs to happen over here is we need to look at, in order to get it to work out what the major product is, we need to put the proton and the leaving group opposite each other. So to do that, we've got two options. I'll just keep the front the same and change the back like I did the last time. So I want the bromine there, so I put it there. By getting there, I move the H over here, and the phenyl moved up to that position over there. And now they are anti-periplanar to each other. So the elimination can occur. I can take my base and I can show it picking up the proton, kicking that in. It's not going onto that carbon, but for me, we're looking at it funny, so we can't see it properly. And we kick that out. And the key thing here is that in the product, these two things over here, the phenyl and the methyl, must be on the same side. And here we see it over here. They're on the same side of the double bond. And the OMe and the H must be on the same side. There's the H over there and the OMe on the same side. And so for E2 elimination reactions, we have to use Got to be very careful here. They are stereospecific, and we have to use a Newman projection in order to figure out which of the two products are. There is no selectivity that's really happening over here. It is rather there's just one possibility. In the last lecture that we'll look at on elimination reactions, we'll go through a lot of different examples and show how regioselectivity and stereoselectivity play out in those examples.